We're starting with this diagram. You're welcome. Okay. So today we're going to continue thinking about filtrate, how our kidneys are filtering blood, how they're producing urine. But we're going to start out with this practice problem about the glomerular filtration rate. When we left off, we were talking about the fact that this is regulated. Okay. So to understand how it's regulated, I want to make sure that we understand what factors can influence it. Okay. So we're thinking about how we might affect this rate with the glomerular filtration pressure, actually, overall. Yeah, okay. The glomerular filtration pressure, the glomerular capillary hydrostatic pressure, the glomerular capillary osmotic pressure, the hydrostatic pressure in Bowman's capsule, the concentration of proteins in the plasma. Hopefully you recognize that almost all of these are referring to various facets of those Starling's forces that we went over last time. Okay, so I'm going to pull up that little picture with our equation for the glomerular filtration pressure, summarizing the directions of those forces so that we can understand these questions. Okay? Okay. So when we're looking at this problem, I'm going to remember first what our GFR is. So the glomerular filtration rate, that's the one where we're thinking how many milliliters per minute are getting filtered into our nephrons, so into the kidney. So that was that one where we had a value of 125 milliliters per minute. That's regulated. That's about 20% of the total plasma that's going to the kidney. But we can have changes to that at extreme conditions. Usually we're tightly regulated in normal ranges of blood pressure. Okay. So while we're thinking about the glomerular filtration rate, which would be in milliliters per minute, okay, all of these questions pretty much are referring to factors that affect the glomerular filtration pressure. Okay, so the glomerular filtration pressure was the one we were looking at, and we were thinking about what are our factors for filtration. So taking fluid out of our glomerular capillary, shuffling it into the nephron, okay, versus factors that fight against that filtration process. Okay, so the reason that the glomerular filtration pressure matters, so the pressure we can see is in millimeters of mercury, just a pressure measurement. Okay. Reason here is that if you have a higher pressure for filtration, right, what we're really talking about is a force for filtration, right? So by definition, kind of, if you have more of a pressure for filtration, so if the glomerular filtration pressure is higher, you're saying that you have more forces causing filtration, driving filtration, which means that the rate of filtration also goes up. So those two things work together in unison. They're different measurements, but they work together. The same factors are going to influence them in the same direction. So in this warm-up, we're just tracking increases. Okay. So if we have an increase in the pressure, say we went from this normal value of 16 to 20 or something, right? The glomerular filtration rate will go up, okay? Because those two things are really directly linked. Go up. Okay. Okay. And we had a small note comparing the difference between our systemic capillaries and their filtration pressures and what's going on in the kidney, right? And we saw that the filtration pressure in your systemic capillaries was like 2-ish, right? And much lower. And that corresponded to a much lower rate of filtration and a much lower daily amount of filtration. That was that comparison of 3 liters filtered per day versus 180, right? So that's another way you can kind of remember the linkage between those two. Okay. So these next 4 factors all have to do with that equation here, those Starling's forces affecting our glomerular filtration pressure. Here. No, we could keep the circle, so I'll just pick a different color. Okay. So first, we're going to think about the hydrostatic pressure of the glomerular capillary. Okay. So we can think of hydrostatic pressures, hydro, that indication water in the word should remind you that's the pressure of the fluid pushing on walls of the container. Okay. So if you see hydrostatic pressure, you then look for, okay, what container are we thinking about? So we're saying here, we're talking about the glomerular capillary's hydrostatic pressure. Okay, so we're talking about fluid in the glomerular capillary pushing out on those walls. Okay, so that's going to be one of our forces for filtration. Okay, so our force for filtration, and it's designated as PGC, hydrostatic pressures, symbolized by that capital P. Okay. So overall, if we increase any force for filtration, that's going to increase our filtration pressure overall, which means we'll also increase our filtration rate. Okay, so we're going to say, I guess it said rise or fall. So we're going to say rise here, right? Because what we've done, so I circled it in the image, right? We increased a filtration pressure. We could also, if we prefer equations, note that that's in this first part of the equation, right? So if this number goes from 60 to 70, right? Overall, your number at the end will increase. Okay, so that's another way you could approach this problem. Okay. So for the osmotic pressures, those are symbolized by pi, okay? They have to do with the fact that we have impermeable solutes in certain places that pull water towards them because they can't cross the membrane, but they still want to spread out. They still want to reach equilibrium across cellular membranes. Okay, so we're thinking about solutes exerting a pull. Now we're going to find out where they are, which is in the glomerular capillary. Okay, so we're thinking about things dissolved in our plasma that are pulling water towards them. Okay, so this is fighting against filtration. Now we can just follow arrows to understand this, right? Or we can find it in the equation. Okay, so this is a force against filtration. Okay, so then we would have a fall in our glomerular filtration rate. Okay. We can then look at Bowman's capsule. So Bowman's capsule being this sort of Pac-Man mouth eating our glomerular capillary. I think this is the capsule. Okay, so again, we're going to look at the hydrostatic pressure, and we're going to be looking at concentration of proteins and other solutes. Actually, we got a tricky one on E there, but we'll walk through each of these pieces. Okay, so now we're thinking about Bowman's capsule. We have a hydrostatic pressure. Okay, so we symbolize that again with a big P. And now we're writing Bowman's capsule, so we can find that in our equation and on the diagram. So that's up top. So what we're looking at is fluid pushing back out. Okay, so that's a force against filtration. Okay, so here again, we have a force against filtration. We're going to have a fall in our glomerular filtration rate. Okay. So here we'll have a fall. Okay. Sorry about my misleading bit about this last one. So our last factor, I, B, C, actually isn't in this question. Okay, what this would, the way this question would be framed, right, would be asking about solutes dissolved in Bowman's capsule. But the solutes we're thinking about as our main impermeable solutes are proteins. They should not, under normal conditions, really get into Bowman's capsule. So the reason that we don't have this here is they're usually 0, but we could have changes. But if they did go up, this is still a force for filtration and GFR would rise. Okay. But what we're actually asking for here, I'm going to clear these real quick. Okay. We're actually only asking about the concentration of proteins in the plasma. Okay, so we're thinking about proteins in the plasma and impermeable solute. So this is really just a partial description of what we had in C, right? So this is just a description of one of the reasons we have that osmotic pressure, that pull this way, okay? So this is a force against filtration, okay? So this is also a fall. Okay. So questions about how we look at this, how we walk through these factors. I'm a big fan of drawing these out. I'm a simple person. I like arrows, but multiple ways to get this information. We try to have pictures, equations, and words for all of the ways of thinking about these kind of processes. Okay. So if you like some of them, just focus on those types of explanation. So long as you get to the right answer, we don't really care how you get there. Okay. So we're starting off with our new stuff on this slide. We're still in that packet about the glomerular filtration rate and the proximal tubule. Hopefully we'll get to today. So what this is showing us is some of the impacts here on your actual body of changes in the glomerular filtration rate, and really some of like why you would want to be thinking about these changes, right? So situations that you might see changes here are a lot of situations that might change your blood pressure, as an example, or change just like the fluid state of your body, like how hydrated you are. So up here at the top of this diagram, you can see that we're tracking through, okay, what happens if you are hemorrhaging or sweating? So your outside is really hot, you're like sweating bullets, right? You're losing a lot of fluid. Okay, so you're actually dropping down how hydrated you are, how much water is in your body. Same sort of thing would be happening if you're hemorrhaging, okay? So this is gonna decrease blood volume, okay? Which overall is just decreasing a bunch of pressures in your cardiovascular system, right? So this is tracking back through some of the things we've spoken about in previous units. So if we see a decrease in blood volume, our overall venous pressure goes down, so the pressure in the veins, meaning that we have less blood coming back to the heart, so less venous return, meaning we have a lower cardiac output, so less blood being pumped out to your body, which means you have a drop in MAP, so a drop in blood pressure, essentially, okay? So we talked about some of the processes that help regulate this, right? We mentioned our baroreceptors before. So our baroreceptors, right, were those pressure sensors, right? So those baroreceptors can sense drops in pressure because it's really important to get your blood pressure back up to make sure that you have appropriate perfusion, so appropriate blood flow for things like your brain, okay? So those baroreceptors respond. One of the ways they do that is with our sympathetic nervous system. So you increase that fight or flight kind of stressful kind of set of hormones, right? Including to the kidneys, okay? So this little bit, we're now focusing in on the kidneys, which we didn't do before, okay? So in the kidneys, the response to that sympathetic nervous activity that we're getting is vasoconstriction of arterioles, right? So we've thought about vasoconstriction before, right? So we're talking about arterioles, they're starting to clamp down, they're getting smaller, their radius is decreasing because of the effect of those hormones, those neurotransmitters on the smooth muscle. So we have that vasoconstriction. We actually do have arterioles when we're thinking about our kidney, right? In general, we pretty much always have arterioles kind of throughout our body, but we've seen two specifically, right? We had our afferent arteriole going into our glomerulus that we've just been talking about, and then leading out our efferent arteriole. And so I'm going to write the A and E, right? So the sympathetic nerves have an effect here on those arterioles, right? So both of these are getting vasoconstricted, right? Which means they're getting narrower. Okay? So when radius goes down, resistance goes up, right? And resistance here is going to have a couple effects. Okay, so we're increasing resistance in our kidneys. So renal means kidneys. So increasing our renal vascular resistance. One thing that happens now is that this adds into our total peripheral resistance, which we just added together. Right, so this is sort of hearkening back to our flow equation, our flow being a difference in pressure over our resistance. And when we were subbing these in, our pressure difference was measured as MAP. Our R, our resistance here, was our TPR, and our flow had to do with that cardiac output, essentially. Okay, so an increase here in resistance, ultimately, when we reshape things, also leads to an increase in our mean arterial pressure, which is a negative feedback loop here. Okay, so that's one way that we're adjusting our mean arterial pressure kind of immediately. But now we can add on this piece about the glomerulus, this piece about filtration. Okay, so really new stuff here is that when we have this increase in resistance, right, what we're saying is we've increased resistance of these blood vessels, which means it's like harder to get blood flow to them, right? That's what resistance is. We're resisting flow, essentially. Okay, so the blood is kind of slowing down going into and out of our glomerular capillary, right? So we should be doing this, but we've made it harder to get in here, okay? So if we have less blood flow going to the glomerular capillary, it's that twisty ball of blood vessels, essentially we're going to end up kind of lowering their pressure as well, right? Which means that that glomerular capillary hydrostatic pressure, the pressure of that fluid out on the walls and into the nephron, is going down. And that was our main force for filtration, right? So ultimately, we've lowered the glomerular filtration pressure, okay, which means that our glomerular filtration rate is going down. Okay, so we're not pushing as much fluid into our nephron, into the kidneys. Because we've increased the resistance of these blood vessels, we're not getting as much blood flow to the kidney in the first place. Okay. This is great because the problem we're trying to solve, right, is that we're either bleeding out or sweating out a ton of fluid and we're losing blood volume, essentially, right? So it's now kind of awesome that we're not filtering out so much fluid from our plasma. So that means we can keep it in our body, right? So when we decrease this glomerular filtration rate, this means there's not as much fluid in your urine, which is the ultimate endpoint, that you're excreting urine from your kidneys and your bladder. So you're not losing as much fluid, okay? So this is also a larger negative feedback loop on blood volume, and a bit more of a long-term one, because we're really keeping that fluid in the body instead of just adjusting our vasculature, right? So we're not just changing the size of tubes, we're actually maintaining blood volume. We're actually physically keeping fluid. So when we talked about regulation of MAP, we said that long-term, our blood pressure is going to be adjusted by our kidneys. And this is sort of the idea behind how that's going to work, right? So in the short term, when we had our reflexes, our baroreceptor reflexes, that was just like tensing and relaxing blood vessels to adjust pressures, adjust resistance. But long term, if we adjust the blood volume, we don't have to change the contraction state of those blood vessels at all, right? We can just actually adjust how much blood you have. Okay. So that's sort of the overall impact on your body and in actual situations, actual physiology of glomerular filtration rate. So I know that was a lot, but that's kind of where we're going and like why we are thinking about these topics partially. So everything we've been talking about so far was about filtration, pretty much. Okay. But that is not the only thing happening as we walk through our arguments. Okay. So we have a couple of different processes that we're thinking about. We're going to be thinking about filtration. Reabsorption is also really important. We're also going to be thinking about secretion and excretion. So those are the four kind of like basic functions or sort of like directional functions of our kidneys. Okay. So the filtration is happening at the glomerulus, up at the top of our nephron. We have fluid coming out of the plasma, so out of your blood, going into the nephron. Then we're going to start referring to it as filtrate. Okay. We're going to talk about it as filtrate, but it is eventually going to become urine after we do all these other processes, after we do the reabsorption, after we do the secretion. Okay, so it's on its way to becoming urine. Okay. So filtration has now happened. We have filtered out 125 milliliters per minute of fluid from the plasma into your kidney. That's like 20% of your blood volume, 180 liters per day. You do not want to leave all that fluid to excrete as urine, okay? So we're going to have to reabsorb some of it or we are going to die, okay? So that's the goal of a lot of our reabsorption. So our movement, just a definition of reabsorption, right? We have our nephron, which is Bowman's capsule, proximal tubule, kind of squiggly, loop of Henle. You're going to have a distal tubule, also kind of squiggly. And we're going to lead into collecting ducts. Okay. So that's the nephron piece, but we also have blood flow all around it. So we had our afferent arterial, we had the glomerular capillary, we have an efferent arterial. Notice this is not a vein. Okay. So that efferent arterial is continuing along, following the course of the nephron. So here we're going to call it paratubular capillaries. So it wouldn't really be a straight line, but I'm going to draw it like that just for our ease. Okay, and then it's going to drop down, follow along. All these things are kind of nested around. Okay. So blood flow is like following with these, all surrounding. Okay. So reabsorption is now going to be movement from our filtrate, so from inside that nephron, back to the blood. So that's what the re is about, reabsorption, because it's been filtered. So the filtration was when we went from the plasma in the glomerular capillary into Bowman's capsule. Now our reabsorption is we're putting some of it back into the blood. We say, oh no, never mind, you want to keep that. Okay. So most of this is going to be happening in the proximal tubules. So this region of the nephron, essentially. We are going to have more of it happening in the distal tubules and the collecting duct when we get there. But in terms of like volume, the bulk of it is happening pretty immediately right here. Most of this is not regulated when we're thinking about reabsorption. And that's particularly true about the proximal tubule. And when I say regulated, okay, we're going to see as we get to the end of our nephron to that distal convoluted tubule and the collecting duct, we're going to see that hormones make a difference. So when I say regulated, I mean like by hormones. Okay, so at the end of this situation, we're going to be thinking about different hormones. But up here in the proximal tubule, this is all going to be about just like transporters in cell walls. Okay, I'm saying this to you for the reason of we are going to be looking at numerous types of active transport. So I just want you to be careful. Regulated doesn't mean like we're not going to use energy. Regulated here means we're not responding to hormones. This is just part of the process that naturally happens kind of all the time in this region. Okay. So our barriers for reabsorption overall in the proximal tubule are going to be our renal epithelial cells and our capillary endothelial cells, which we'll take a look at a picture of, but all that's saying, right, is that you have a cell here. That's the renal epithelial cell, the lining of the tubule here. And you have the lining of the capillary, right? So we have to get across these two cell layers in order to get back into the plasma. Okay. Cool. All right, so this is a list of the normal rates of filtration and reabsorption for water, and also a bunch of solutes. Okay. So starting with water, I've said a couple times, right? 180 liters per day are filtered. So filtered go into the nephron, into the kidney for this whole readjustment process. You can see 178.5 liters per day. So most of it is pulled back into your plasma. So most of water gets reabsorbed. Okay. Percentage-wise, 99.2%. For our other substances, the main one we usually talk about, because we often think about things like diabetes when we think about kidneys, and in general, your sugar levels in your blood are important to you. Okay, so for glucose, you have 800 millimoles per day being filtered into the kidney, so into the nephron. Your reabsorption rate is also 800 millimoles per day. Okay, so note you are keeping 100% of your glucose if your kidneys are functioning normally and your blood sugar levels are within a normal range. Okay, and that should intuitively kind of make sense, right? The reason you have glucose in your blood in the first place is you ate something for energy. You're going to take that glucose, you're going to use it for metabolism, right? You're going to break up that glucose and turn it into ATP. So you don't want to pee it out, right? There would have been no point in absorbing it if you were going to pee it out. Okay, so you want to reabsorb that entirely. And we have a lot of other solutes that we are adjusting. So many of them are reabsorbed significantly. So you can see sodium mostly gets reabsorbed, chloride gets reabsorbed, bicarbonate, and so on. But we're going to really want to make sure for our practical purposes of understanding normal function in diseases, I would say water and glucose are our two best examples for understanding the processes happening on here. So that's your bang for your buck is going to be those two. All right. So we are now thinking about what's happening in the proximal tubule, about that non-regulated reabsorption. Okay. So just orienting. So here was our glomerulus where we were talking about filtration. So proximal tubule is just the next thing. So proximal, just like proximal in anatomy lab, means near to the beginning, kind of. Okay. So proximal tubule is the first thing you hit. And we have paratubular capillaries. So we have blood flow continuing along the nephron here. So we think about our proximal tubule as our mass reabsorber because it's doing most of the reabsorption. That's all that means. Okay. So it's reabsorbing 70% of the sodium and water that you're ultimately going to reabsorb. And it's doing 100% of the glucose reabsorption. So that glucose that just got filtered by the glomerulus, your body is immediately snatching that back. Okay. Wants that back right now. So that's going to happen at the proximal tubule. So we can see what these cells look like. Okay. So when we're thinking about the cell layer, here, this is our proximal tubule epithelium. Okay. So we have our individual cells. So we have our basolateral membrane down here at the bottom. So basolateral, think base, lateral sides, versus our apical membrane. Okay. So the apical membrane is going to be next to our filtrate. So our filtrate eventually becoming urine is going along here. So this is kind of lining the tube. The basolateral membrane is facing where we'll have our capillaries. Okay. So that's the arrangement we have here. We have tight junctions between the cells. So a tight junction is supposed to kind of create a seal in a layer of cells, right, to prevent things from crossing. But we have slightly leaky tight junctions in the proximal tubule specifically. So we're going to see that some things actually are going to be able to cross between our cells. So that's what paracellular transport is. So we're saying that things, some of them are going to be able to cross between those cells. So that's what the structure of this wall is going to look like. So here you can see those same features in cartoon form. So here's that basolateral membrane. Okay, here's that apical membrane, and here's our capillary. So as we talk about reabsorption, we are going to be thinking a lot about sodium again, okay? And we're going to be thinking about our sodium potassium pumps, okay? So sodium really is a huge driver of all sorts of functions in your body. Right? We saw especially its role in our neurons, right, and in our nervous system, but it's doing important stuff all over the place. Okay, so I'm going to point out to you here that on that basolateral membrane, we have sodium potassium pumps. Okay, so we're looking at that sodium potassium pump and we're thinking, this tells me something about my sodium gradient. Right, so the sodium potassium pump is pumping sodium out here. So it's creating a higher concentration of sodium here in the direction it's going. Okay. Right. And it's creating a low concentration of sodium here inside the epithelial lining of our renal tubules. Okay, so low sodium here. So this is really important because this means we've set up a gradient that we can use to move other stuff, right? In order to remove, I'll just make a point, right? So remembering our types of transport, right? We had passive transport, which meant we had molecules going down their gradients or going along with their electrochemical driving force if it's something that has a charge on it. We thought about that in A&P 1, okay? So that means they go from high to low. But if we think about glucose, right, we just said we're reabsorbing 100% of it, right? So we are creating a very low glucose environment in your filtrate and then in your urine. So we cannot do that by passive transport. We're going to need to use energy. We're going to need to use active transport. The type of active transport we use here is going to be secondary active transport. So our two types of active transport, we had our primary active transport, where we directly use ATP. And then when we have secondary active transport, what we're doing is we're using the gradient of some other molecule in order to pull along a second molecule, right? So you're thinking about it like someone going through a revolving door, right? If someone steps in behind you in the next section of that revolving door, if you're still going, they're going to, okay? So something like that. That's our secondary active transport. So that's what happens with glucose and sodium. And sodium in general in your body does that with a lot of different molecules, okay? So we've created this sodium gradient, okay? Created this sodium gradient. So we have low sodium here, high sodium in the tubular fluid, okay? So that sodium is now going to go down its gradient, easy peasy. So that part is in its favorable direction. If it was just sodium moving, that would be passive transport. But you can see that this transporter is also carrying glucose. So in this situation, glucose is coming along with it. Anytime we see a red arrow in your physiology diagrams, that's actually telling you that it's active transport, that's an unfavorable direction, red for no, green for yes. So green is always symbolizing the passive direction. So glucose here is moving against its gradient. So we could even draw on that we now know that this is actually a high glucose environment compared to a lower glucose environment in the tubular fluid, eventually getting all the way down to 0 glucose in that tubular fluid. Okay. So this is an example of secondary active transport. Okay. So once we have that high glucose here in our renal tubule or epithelial cell, it will ultimately be able to go down its gradient and move towards our capillaries and back to the blood. So our sodium is a driver for the reabsorption of glucose, and in general, reabsorption of other things too throughout your body. Anybody who took bio of the cell as their prerequisite for this course may or may not notice that we have just walked through one of your problem sets from last year. So, which is why you guys had that problem set. Okay, so when we're thinking about the movement of glucose or the movement of other substances, but glucose is the easiest example and also the most relevant to like patient care, okay? There's only so much glucose that a transporter can actually carry, right? You have a limited number of these proteins embedded in a cell wall, and at some point they're going to be full, right? So if we're thinking about this, right, if we have our cell, just going to draw the apical membrane, our tubular fluid here, right? So say we have 3 of these transporters, right? If we have 4 molecules of glucose flowing past, okay, you got 1 space here, you got 1 space there, you got 1 space there, but there's nowhere for this 4th glucose to go, right? So that's what we mean when we say these transporters can get saturated, and that's what we're talking about when we're talking about a transport maximum. What we're saying is that at a certain level of glucose in the plasma and therefore in the filtrate, you will have so much glucose that all of these transporters get full, and then you will have glucose spill over into the urine. So that 4th one's going to continue throughout your nephron, was supposed to get absorbed in the proximal tubule. That's where glucose reabsorption happens. It didn't, so now you're peeing it up. Okay. So when a solute that should be transported across that epithelium gets set, saturate those carriers, that is our transport maximum, and we hit a renal threshold. So the renal threshold is going to be essentially a concentration of that solute that should normally be 100% absorbed, but the renal threshold is like the concentration where you actually can absorb all of it. So if you go above a renal threshold, so if you have more glucose in your blood than we have space in that kidneys to reabsorb it, you'll have surpassed the renal threshold and you'll have this spillover. Okay. So if we go above the renal threshold, you see solute, in our case, glucose in the urine. Okay. So that's what's going on here. Okay. So the transport maximum, the reason we have 2 words, the transport maximum is kind of referring to it from the level of the carrier itself, right? So that's referring to like kind of how fast they can transport this stuff. The renal threshold is a concentration of a solute, so like a blood concentration of glucose. Okay, so we'd have a speed, and this is going to be a concentration. So our best example for all of this is glucose. Glucose should be freely filtered at the glomerulus, meaning it's all going at the same concentration as it is in the plasma into the filtrate. Okay, so we just multiply our glomerular filtration rate by the concentration of glucose to get our filtered load, which is our amount of glucose in the filtrate, right? The amount that has gone into the kidneys every minute. Normally, it's all getting reabsorbed. No glucose appears in the urine. If these carrier proteins are full, we hit our renal threshold, we start to have spillover. So we walked through in the picture before how glucose should be transported usually, but what I was telling you in words is that at the apical membrane, right, so the side facing the filtrate, we had secondary active transport. That was the bit where we were using that sodium gradient. And at the basolateral membrane, which is the side facing the blood, we'd ultimately have facilitated diffusion, which is a type of passive transport. Okay. So when we're thinking about the renal handling of glucose, so renal kidneys, so how your kidneys are handling glucose, our plasma glucose, typical value is 100 milligrams per deciliter. We find our filtered load, we get 125 milligrams per minute. We calculated that out on Monday, or we looked at the calculation. I'm not going to be making you remember, yeah, I'm not going to be making you do a bunch of calculations on that. Okay. So we just filter 125 milligrams per minute of glucose, but we have a transport maximum. Okay. So our transport maximum, the maximum that our carrier proteins can handle, is 370 milligrams per minute. Okay. So that's like how fast they can handle taking glucose into these cells. Okay. So if you have more than that, right, so we have our filtered load in milligrams per minute, we have our transport maximum in milligrams per minute. So if you have more, you are not going to be able to get that extra glucose into the body. Okay. So we can then calculate pretty much backwards to find out what plasma glucose level corresponds to this transport maximum. Okay. So that's how we would find our renal threshold ultimately. Right. So our renal threshold is what plasma glucose level of what plasma glucose level of glucose, right? What concentration is going to hit that transport maximum. That's how we get our renal threshold. And the actual value is 300 milligrams per deciliter. Okay. I don't really need you to actually do that calculation, but I do want you to just like kind of understand on a, sort of intuitive level how these numbers are associated with each other. Okay. So we have a value for glucose, we get over it, we hit the transport maximum, which means we excrete glucose. Now, it is the case that our theoretical renal threshold, so the one we might calculate out if we wanted to based on our transport maximum and understanding how filtered load works, okay? Our theoretical threshold should be 300 milligrams per deciliter. But in real life, if you're thinking about this glucose traveling through the tubule, right, they're not all in a straight line and they're not all bumping into the membrane, right? You have some here, you have some over here, you have some over here. Okay, so if you have tons and tons of glucose, some of it is kind of traveling like too fast to come into contact with an empty carrier. So if you have high levels of glucose, some of it will just go straight on through, even if technically you could imagine, say there were a carrier way down here, right? Just by luck of the draw, maybe your extra glucose doesn't get all the way down there and touch it. Okay? So your actual renal threshold, so like the actual value of glucose in someone's blood where you start to see glucose in their urine, is much lower than the renal threshold theoretically is. So the actual renal threshold where you actually start to see glucose spillover is about 160 to 180 milligrams per deciliter. So that corresponds to a filtered load of 225 milligrams per minute. So here we see how these things are kind of related in graph form. Okay. So what we're looking at here, we're looking at plasma concentration of glucose. So blood glucose levels, essentially, how much glucose is in your blood. So this is just a concentration. And we're looking at how fast is the glucose moving over here. Okay. So this is in milligrams per minute. All right. So for filtration, we have a pretty much one-to-one line. Okay. So if you have higher amounts of glucose in your blood, there's more movement of glucose or filtration. So if you increase the plasma concentration of glucose, more glucose is filtered into the kidney. Okay. So this is just a straight line. It does not matter how high that glucose gets. If you increase glucose, more glucose goes in the nephron, up and up and up and up forever. Okay. Right. So that's filtration. So you're just going to get glucose out of the glomerulus and into the nephron. Reabsorption and excretion are different. So the reabsorption is what we just walked through happening in the proximal tubule. Okay. So if you are at low concentrations of glucose, it looks just like our filtration line. right? More glucose gets reabsorbed, right? More plasma glucose, more glucose reabsorption until we hit our renal threshold. So here we can see we've marked it down at about 180. So this is our actual renal threshold from that previous slide. Okay. So at our actual renal threshold, we start to see that we're starting to have less reabsorption happening. Right? It's still more than if we had a lower glucose level, but it's not increasing as quickly. And we're starting to have some spillover. So the spillover is the excretion. So we're starting to see glucose in the urine. And when we hit the transport maximum of glucose, right? So the maximum amount of glucose that totally saturates those carriers here. And then we hit our transport maximum. Okay. We flatten this curve. We now reabsorb only that amount. Those carriers are saturated. Absolutely no more increase in reabsorption. So we start to see excretion rise. Okay. And now once we hit that point, that transport maximum, this line would just continue on the same way the filtration line does, because all of the glucose above that line is now getting excreted out. It's all spillover from here on out. And we will stop there. Great point, because we've finished everything to do with that glucose. So next time we'll be talking about water. Okay. So we're not moving on to the water slides quite yet, but that's going to be the next section of the reabsorption, and we will move on to that next slide set. Right, probably.